Hello, I'm Bill Allan. I'm the casework supervisor at Cybergenetics. Cybergenetics is the creator of the TrueAllele software, which I'm going to be talking about today. So when I was preparing this talk, I was thinking about the multiverse. And if you don't know, the multiverse is where there are different versions of like a universe or a person or a thing. And that analogy, I'm going to try to use that analogy today to look at some things. I actually use this in court. I'm trying to explain a large number. And let's say there's a match statistic of something, and then we have an error rate of 1 in like 100 billion. Well, what does that mean to a jurist? Like, what does that mean? So if we talk about, like, maybe on the planet Earth, we have 10 billion people. If we're looking for somebody with a match statistic of that value or higher, we'd have to go through 10 planet Earths. So again, trying to explain things to a jury, I've actually invoked the multiverse for better or worse. I even saw somebody walking around with a shirt saying, "Be the best version of you that you can be." And we heard the keynote, and maybe that follows on with that. So let's talk a little bit about science. So in science, we have physical laws. And one of the good things is these physical laws are universal. And this is a good thing, is because this allows us to not only look at like incredible distances, like the Webb telescope they're saying that they're looking at the atmosphere of an exoplanet 163 light years away, and they're saying they can identify methane in that atmosphere. That's because of all the math and science, but chemistry. It's the same over there as it here. When NASA shoots up some kind of probe or some kind of spaceship, they're using all of these different equations to figure out how to smash the thing into an asteroid. Again, so this is a good thing. And these things also go back in time. That's how we can know about the past and make inferences about the past. But what about DNA forensic science? What are the laws there? So I have some words up on the screen, like we could talk about like genotype, how mixture weights are identified, likelihood ratios is a match statistic, inclusion and exclusion. Maybe the only thing we really can agree on is that we all have DNA, and that DNA can be used to identify people. But we're going to see there's some differences. So we're going to start at laboratory. So as part of my analogy of the multiverse, think about all the different forensic DNA labs across just the United States. I'm sure there's more than 10, probably 100, 200, whatever it is. There's multiple labs, both public and private. What do they do when they have touched DNA? What do they do when they have DNA that is damaged? What about when they have a complex mixture? What is the outcome of that data? What if the data is just too old and too destroyed? What if the mixture is known to contain biologically related individuals? So we have this difference in like what the lab is going to do. But let's say that data is going to get into the lab. Now, as we actually just heard, there are different extraction processes, even within the same lab. There's different STR kits. We have, there's ones from Promega, from ABI, Kaigen, and I'm sure there's other ones. We have our PCR product. We're going to put it on a sequencer. We're going to separate it. There are, maybe for the older generation, you may remember slab gels, like the 377. There's also, now we have CE, or capillary electrophoresis. We can actually look at NGS data, which is a completely different thing. So that's how we're separating our data. So now we have our data signals. What are we going to report from that? And are we going to calculate an error rate? Again, for each laboratory. And then there's the methods that those laboratories are using. This is 2024. I'm hoping that most labs have moved away from a manual way of interpreting data. Again, just because we do have computers that can help with that. Typically, manual methods are less informative. But anyway, so that regardless if it's a manual method or we're all using software, that software may incorporate a data threshold. And now we're going to say, well, for new software, some software requires calibration. So let's say we're calibrating our software on our data from 2020, and now it's 2024. What does that calibration mean? Has our data drifted away from that? Should we calibrate again? And then there's other parameters that go into our software. What do we do about stutter? And then lastly, how does actually the software work? How does it compute what ends up being, like, say, the results? Okay, so then as you look around the room, we have different analysts. And analysts have their own differences they bring. Not everybody went to Duquesne University. There's other schools of forensic science. When they work in maybe a forensic lab, they receive different training. Their experiences are different. Like the person who walks in day one getting ready to use their pipetter is different from somebody who's maybe going to leave that field. And again, the different systems and their own different preferences and just their innate differences. Everybody's a little different. Like somebody might be, just as a person, they're more methodical. So now we're going to talk about the outcome differences. So now we have our data, it's been collected, it's been extracted, it's amplified, and it's run out, and we're now going to interpret it. So is there going to be an inclusionary match statistic? Or is our lab, do we report exclusionary statistics as well? What is that match statistic? Even if it's, using a manual method like CPI, like the combined probability of inclusion, it's still a likelihood ratio. So we have likelihood ratios. But then there's these things here at the bottom. What if our lab says if it falls below a certain thing, it is uninformative? Or it's inconclusive, we can't provide a statistic. Or no comparison can be made because the data is too low, too complex, or too whatever. So how is the lab going to report this? And again, the labs using the same kits, sequencers, and software could have different conclusions at this step based on what the lab does. Again, I don't think anybody here, actually, this is not news. I'm not breaking new ground here. Because here we have like the Mix 05 study. We have the Mix 13 study, and then I have a little image of the Mix 2021 study. We know as a community, we're getting different answers. Again, it's been almost 20 years now from Mix 05. We're getting different answers. And this is why I have the title that I do about why I'm thinking about the multiverse. Because if you think about it, in either different universes or different labs, we take the same DNA evidence from the crime scene and it goes to different laboratories. In one laboratory, we have an inclusionary match statistic that results in somebody going to jail. Again, they don't get shoes in that jail, but they're going to jail. That same evidence processed in another lab, there may be a statistic, but maybe the statistic is cannot be excluded from the major contributor, can't say anything about the minor contributors. So in that multiverse, that data, the opposition might be able to use that information to have their defendant exonerated. And then there is data that is not even processed. Like, you'll hear more about this tomorrow, about cartridge cases, but sometimes the lab will just say, this data, it's not even worth processing because we're not going to get, with our current process, we're not going to be able to get any information from it anyway. So what's the point? This prompted me, again, to give the title that I did. It's so many different outcomes from that same DNA evidence. So now, talk a little bit about TrueAllele. TrueAllele, as I will show, again, this is where we're going to start, brings a lot of sameness to that. And I'm going to show you that. So here, again, talking about the different aspects of forensic DNA. You can read here. And then we have our different people. The last equation was actually force is equal to mass times acceleration. This is actually a real equation. This is data is just a product of the genotypes times the weight of those genotypes. And just as a quick explanation, what that means is, again, this is maybe not news to this crowd. So if I have one person's DNA signal, this is my alleles, my fingers here, and we have another person's alleles, and that's their signal there. And if they were mixed together, we'd have a different pattern. It would be additive. So the data would just be the genotypes plus how much of those individuals were added. And of course, because of PCR, there's some variation. But again, I'm going to use, the reason I wanted to explain that to you is because I'm going to talk a little bit about how TrueAllele works. So here we have, we're just going to talk a little bit how TrueAllele works as a software, as a probabilistic genotyping software. So it does not require calibration. It just learns from the data. And how it does that is it uses Bayesian inference. And maybe you've had that in statistics or in a class on that. But if you didn't, all Bayesian inference is how our brain thinks. You start with a prior, some prior information. Here I am in Pittsburgh. There's a probability that the weather's cloudy, it's raining, sunny. There could be a tornado, maybe there's a sandstorm. Some of these possibilities are less probable than others, but they're all possibilities. So then I walk out these back doors here and I look out the window and I see, well, it's Pittsburgh. It's probably raining but whatever it is right now, or it's cloudy. And now I've updated my belief. Again, I just started with just some basic priors, got some data, used the data to then update my beliefs. And that's how Bayesian inference works. So again, talking more about the software, it doesn't have any thresholds. It goes all the way down to baseline. It looks at all the data. And all it's doing is, if you remember that DNA pattern I was using my fingers, it's just trying out patterns that explain that data. Patterns that explain the data better end up with more probability. Patterns that explain data less with less probability. And it separates out the DNA contributors. There's no conditional, it's the victim and the suspect and one unknown over the victim and two unknowns. It's just separating out the genetic types up to probability, and then they can be used for comparison. It also calculates an accurate likelihood ratio, and we showed that by, again, maybe this is intuitive, but if you contribute a little bit amount of your DNA to a mixture, you're going to have a smaller match statistic. If you're the major contributor, you contributed more of your DNA, you're going to have a larger match statistic and everything in between. And again, it had been validated up to 10 contributors, 10 unknown contributors. And then to quote, this is from my coworker, also an author, or co-author, Matthew Legler. He says it's like using a calculator, just as an analogy. All right, so now to get to the actual study. So here we are, we're going to talk about the TrueAllele proficiency study. So back in 2020, we wanted to see if our TrueAllele analysts, we could show that they were proficient. That was the first goal. The secondary goal was to see what are the differences across these TrueAllele labs. And so we had 10 TrueAllele's in the United States participate and a total of 32 trained analysts. So the study design was that each of these 10 labs was in a mixture sample. And that mixture sample was what they created in their lab, either from validation data or from its actual casework that had been adjudicated. And this was supposed to be just representative data, just something they typically saw in their normal casework. So then they also had to provide a matching reference so we could calculate an inclusionary match statistic. And they sent these mixtures to cybergenetics. We anonymized them, anonymized the references, and then analysts signed up to participate. What part of the study was, what the protocol was we're going to send these mixtures samples out to the analysts, again, from 32 from 10 different labs. And their job was to process the sample using the software. Once all that processing was done, they then received the reference samples for comparison. Now, we did that just to show that they didn't know who they were looking for, and also to demonstrate that the computer doesn't need the references in part of its process. But we did it, again, just demonstrate that fact. And their job was to return this sample, match this reference, and give the match statistics for that comparison. So here's the SDR kits that were used in the study. Again, we had many global filer samples and some of the other Promega ones. We've had PowerPlex 16. That's actually cybergenetics data from way back. This data was sequenced on what you can see here, where most of them were in the 3500. Again, the 310, if you don't know, is a single capillary instrument. Again, that was our data. And then we had asked for mixtures that contained at least 3 contributors. Most of the mixtures in the study had 4 contributors. So again, the analyst task was to create computer runs for each of these 10 mixtures. We asked them to do it in triplicate so that we could also look at the reproducibility. So in here, just if you look over there to the right, that's just a picture of that part of the process in the software. And then once all that processing was done, they were given the references for comparison. Again, their job was to use the software, again, some pictures, to say this sample matched this reference and give the match statistics for each of the 3 runs. So if I'm doing my math right, that would be 30 match statistics for each analyst. And so with over 30 analysts, that's like over 900 data points that we're going to actually look at. So now the results. So now we're going to look at the statistics for, first of all, we're going to look at 8 of the 10 mixture samples here. And this is my box plot. So across the x-axis here, you can see those are the names of the samples. And my y-axis is, this is the log of the likelihood ratio, or the match statistic, or as I was saying, the number of zeros, where 6 is a million, 9 is a billion, and so on. So what we're seeing here just overall in these mixtures is that some had less DNA information, some had more DNA information. And this ended up correlating with the amount of the contributor. The low end was about 18%, like a person was 18% of the mixture, where if you can guess it's that case up there at about 30 zeros, which is about a non-million, they were a major contributor. But most of them were in between. We didn't have any very, very minor contributors. So then if we're going to look at one of those cases across the 10 laboratories. So my A through J here, that's representing the 10 laboratories. And again, my y-axis is just showing the log of the likelihood ratio. So what you can see here from my box plots is that everybody visually is getting the same answer. So you think about this. One of these labs, you're processing your data. If you're your lab, you're processing your data, but you're processing data from 9 other laboratories, from their extraction process, their PCR process. Maybe like you use 3500 Fusion 6C, and you've got 3130XL Global Filer, whatever it is. You're processing other labs' data. We can see nobody's excluding anybody. And again, the statistics visually look similar. And then, of course, we want to do some statistics on this. So if we look across the laboratories, we did an analysis of variance. And maybe you remember that statistical test. Again, just looking for variance across all these different data points in consideration of the lab. Maybe you don't remember statistics, but you probably remember the p-value. I know it's already been at least one talk today. We're always looking for significance in science. Like if we're testing a drug or something like that, is it different than placebo? Or is this something different from that? What we're showing here is the p-value for this analysis is 5 times greater than where we would consider significance. So statistically, this is showing that there is no difference in any of these labs processing each other's data. So that's why we have anyway, anywhere, that these labs can process each other's data across, again, this was across all the cases. So then let's zoom in a little bit more and we'll look at the analysts. So here is that same case across the 32 analysts, again, 1 through 32. And if we look at the axis again, this is just the match statistic in band or number of zeros. So here, the colorful chart shows the variation in all the different analysts for their match statistic. And maybe you're seeing this, you say, well, there looks like there's more variation there. And I would agree with you. Because the software, like many modern softwares, uses something you may have heard of, Markov chain Monte Carlo, or MCMC, which is just random sampling. If you think about PCR is a random sampling thing. So just like in that process, when the computer's working out the different possibilities, it's using some randomness, so we're going to expect some variation. But, I mean, again, we're looking at this visually. Let's look at it statistically. So we're going to do that same test, again, the same ANOVA test. And again, we're looking at that p-value. Well, what we're showing here is that the p-value across all the analysts, all 900 and some data points, is closer to 1, meaning that they're all the same, than to the value of 0.05, which would mean they were statistically different. So what this means is any one of these analysts, as long as they were like trained, and I'm not even sure about that, I think I could give you 5 minutes and we'd be doing this, that they would get the same answer on everybody else's data. So the conclusions of the study were using this software negated all of the differences that were generated in the lab. Again, if you go back to that slide where I had the person in and out of jail, different labs processing that same data, different outcomes. Here we've gone the other way where we've taken even different data and we all get the same outcome. And again, we've negated all the differences between the analysts because as long as they can push some buttons, they're going to get the same answer. So the significance of this, is, again, comes back to my title is Everything, Everywhere, All at Once. I'm not sure about the all at once part, but everything, everywhere. We're getting the same DNA answer. Any lab can process any other lab's data from, again, older data to the most recent. This would mean, scientifically, that all the validation studies, of which we have over 40, would apply to all different laboratories. And the reliability also would apply to all these laboratories. Again, as long as the trained analysts are showing that they're all getting the same result, so we have a very reliable method. Something that I think could open up some things where, to me, this would mean that a laboratory could process its legacy cases, which is some of the cases we get. A lab may have validated even TrueAllele software on, say, Global Filer, but back in the day they used Identifiler. There's no scientific reason they couldn't go back and just use that because, again, Identifiler is a validated kit. And then lastly, what this does, this gives me some confidence. Like, so tomorrow I'm going to be testifying about statistics in court that I use TrueAllele to get. And as part of our disclosure process is we hand over all our materials, all our files, the software, access to, to testing of that. I know that if the opposition were to run that same data, they're going to get the same answer that I'm going to be testifying to. For more information, we have a website. I'd like to thank MAPS for letting me speak.